Okay, so the camera's rolling. So I'd like to thank the organisers for inviting me to discuss this paper. So let's get started. So first one, I want to spend a bit of time about the bigger picture. This credit spread puzzle, why don't me and Peter spend, years of our lives thinking about these things. Then I'll talk about what we know about this puzzle. Then I'll kind of try and summarise the paper and give some comments. So I just want to stand back, start thinking about firms. So credit spreads basically come from bonds which are issued by firms. So why do we care about firms? So a fairly obvious question. So they provide employment for us. We have jobs. When they grow, the economy grows. And that's presumably good for the welfare of human beings. You find some people who disagree, but probably not here. And so once you think about it, okay, it's pretty natural then to care about the risks impacting revenues, costs, profits, etc. And also it's quite natural to start thinking about the various characteristics of firms and how they change over time. Both for individual firms and also, very importantly, for the distribution of firms, both across sectors and the economy. So what's that got to do with credit spreads? So let's start thinking about just a bond issued by a firm. So let's think about an individual firm I. It's issued a bond which matures at date capital T in the future. So time now is little t. And this firm could default at some random time, tau I. Yeah? And if the bond isn't paid, then that's it. So you don't get anything. I'm just assuming zero recovery, just for simplicity. So we can very easily compute the date t price of this zero coupon bond, which matures at this date uppercase T in the future. And it's issued by firm I. And basically, it's basically a zero coupon discount factor. That's the, I'll try and press the right thing. That's this equivalent risk-free bond, just a zero coupon discount factor, multiplied by this term here, which is 1 minus the risk-neutral default probability. So you can see the bond is worth less than the equivalent risk-free bond because of the possibility of default. Importantly, what matters here is the risk-neutral default probability. And you can then, using the standard definition of what a credit spread is, you can write down the credit spread for this bond. And so basically, it's just minus 1 over t times the natural log of 1 minus this risk-neutral default probability. Then you can do some interesting things with that. So one important point is that it's very important both in Peter's paper and prior literature is the empirical data focuses on a mean credit spread. Basically from a portfolio of bonds taken from firms where the credit rating and the maturity are fixed, for example, treble B and 5 years. So what I want to be very careful about this. Here I'm writing down basically it's an average credit spread over the bonds in a particular portfolio. And I'm going to call this a cross-sectional mean, which is fairly standard in literature. And just so you don't see these summations everywhere, this bold E denotes the cross-sectional mean. So basically, if you just had 2 bonds in a portfolio, it would just be an average of the spreads. And so then you can basically say, okay, look, we know what the spread looks like for basically a single bond. So we can then compute this cross-sectional average. It's basically this cross-sectional average of the log of 1 minus this risk-neutral default probability. That's quite nice because the log of 1 minus x has a very simple expansion, which is valid when this of x is basically less than 1. And luckily, risk-neutral probabilities are less than 1. So you can write down basically a series expansion which converges. And then you can see very nicely that this cross-sectional average, which is what is reported in the data, basically adding up the average spread across, say, all treble B bonds of particular maturity, it's related basically to the cross-sectional average of the risk-neutral default probabilities, but also the cross-sectional average of the square, and then you'll get the cube and so on. So basically, all the moments of the cross-sectional distribution of risk-neutral default probabilities matter for this cross-sectional spread in the data. So you can see it very clearly here. So you might think, well, okay, well, so what? Well, I'll get to that. So you see this kind of, well, I think it's a nice expression, but it's basically, if you look then at the credit spreads for a particular rating, they encode a lot of information. They encode information about the cross-sectional distribution of these risk-neutral default probabilities for a portfolio of firms and at various maturities. And they're also going to give you the term structure of credit risk for a portfolio of firms. And if you think about what matters for default, well, various characteristics matter for default, the value of the firm, leverage, volatility, and that's going to impact these risk-neutral default probabilities as well. So the distribution of firm characteristics there's going to be a lot of information about that in this credit spread. And furthermore, if you think about the fact that this is there's a capital T here, this is a cross-sectional average basically for bonds issued with different maturities. So not only is it about the distribution, it's really about the time evolution. Information about the time evolution of the distribution of firm characteristics is going to drive differences in credit spreads across maturities. So if you are interested in firms and the kind of risks they face, there's a lot of information about basically the first slide in these credit spreads. So that's why it's, I think, important to look at credit spreads. It's not just important for people who have to buy bonds, it's important for economists. So the credit spread puzzle, what is this thing? So what is this puzzle? Why do some people think there is a puzzle? So if you think about the data, in the data what's reported basically is a cross-sectional mean. When someone tells you, look, the treble B credit spread is such and such relative to treble A, that's basically looking at a portfolio of treble B bonds for a particular maturity and adding up the spreads, taking the average. So that's the cross-sectional mean. So it would make sense then if you were going to think about understanding this, you'd have a model where you also construct a cross-sectional average. And you saw the expression I showed you earlier on, where you basically we had the credit spread written in terms of this risk-neutral default probability. That's the kind of thing you can get from a model. So this is a very simple model. So barely a model at all, kind of a pseudo model. Now what I've done here is basically, if you compare this with the expression I showed you earlier, if you compare it with this, I'm making sure I'm taking a cross-sectional mean, so the bold E appears. And then I'm going to introduce a physical default probability. So basically, I'm going to divide this risk-neutral default probability by a physical default probability. And of course, if I divide by it, if it's not actually there, I've got to multiply by it. So basically, now you can start thinking about how we match these kinds of models to the data. So if you want to put conditions on a model, it would be sensible to say, look, this physical default probability had better be realistic. The first thing. And a credit spread puzzle, how does it arise? It arises if we cannot match the average credit spread for a particular rating and maturity with realistic physical default probabilities. Basically means something about this ratio of risk neutral to physical default probabilities is not right. That's when the credit spread puzzle arises. And of course, this puzzle can exist for various ratings and at various maturities. So we know actually quite a lot about how to resolve this puzzle. So the first thing is that we know that realized defaults don't actually tell us much about expected defaults unless you have a lot of data, a long time series. So basically, if you think about matching expected default probabilities from a model to realized default probabilities, it's actually quite a dangerous thing because the realized default probability is not necessarily it's not a good estimate of the expected physical default probability. And the intuition for this basically comes really from Merton. So Merton, back in the day, told us, look, if you want to use stock price data to estimate expected returns, you need a lot of data for that. You need a long time series. And it's basically the same idea here. But we can get some of that long time series. We can remedy this problem basically by getting a longer time series from the data and comparing it with simulated default probabilities from your model. So I've got a paper which does this, and the data is basically, I didn't get it, I got it from a paper. So we know about this problem, and there's work in the literature which basically deals with it. So the second thing is this failure of the representative firm approach. We know about that as well. This actually has long roots which go back into economics, and I'll talk about that later. So given the way I've presented things, I hope it's obvious that you shouldn't try and match an empirical cross-sectional mean with a credit spread from an individual, i.e. a representative firm. It would seem like an odd thing to do. And to see why it's an odd thing to do, just think about a very simple case of two bonds, and with their credit spreads, let's just take their average, with weights half-half. Well, if these spreads, think of them as a function of a characteristic such as leverage. It's intuitive that spreads depend on leverage. And actually, spreads are convex functions of leverage. So we know from Jensen's inequality, this thing on the left-hand side, which is what basically you have in the data, is going to be bigger than what you get if you just take a single representative firm and plug in the average leverage inside that. So you get this Jensen's inequality bias. If you use an individual firm, it basically dooms you to low credit spreads relative to the data. And Alex David has a nice paper looking at this. So, and for both simple structural models and also for models featuring macroeconomic risks of credit risk, we actually know quantitatively how big this problem is for various maturities and credit ratings. So hang on, going too far. So this paper, I've got a couple of papers looking at this. So we even know that the same statistical aggregation problem impacts models of equity returns and the equity risk premium, provided that you have equity returns as functions of leverage. So how do you deal with this problem? Well, one way of dealing with it is to say, look, let's not use a single firm or a single representative firm. Let's model a cross-section of firms instead. And that's what work in the literature does. And this approach of dealing with this kind of bias has been applied in other contexts by several other people, and I'll mention them. So what does this paper do? This paper uses the same main ideas as the BKS paper. It matches simulated physical default probabilities from the data with realized default frequencies, uses this important idea of modeling a cross-section of firms to match the cross-sectional mean credit spread in the data. And this is why the credit spread puzzle is a myth. Yeah? If you take this representative firm approach, you're doomed to basically make a mess of things. And then you can try and get around it by various fixes, but it's better to do things right in the first place. Now, this paper spends a lot of time documenting how strong this Jensen's inequality effect is for different horizons and ratings, but we already know a lot about that already. So I've got some work basically looking at the size of credit spreads based on a cross-sectional model for treble A, single A, treble B, single B, and so on, debt for 5 and 10-year horizons. But this paper does something interesting. In addition to these two horizons, it looks at this bias for very short maturities. And it would be nice to know how much this adds to our understanding of credit spreads. And I'll talk a bit more about that pretty soon. I don't have much time. So there are some nice things in this paper, certainly not in the work I've done. I've not seen them elsewhere in the literature. This paper derives the variance of the estimate of expected physical default probabilities analytically. It also has nice results on the time series variation in the model-implied cross-sectional spread versus the data, which Peter showed you. And also, the data is very nice. They match the model to transaction-level data over time. And when we did this, we actually used firm-level leverage data. Basically, it's pooled. Obviously not as good. So what I would comment, first I would say you want to exploit and defend your main results. So in this paper, they use realized default probabilities to estimate expected physical default probabilities. And that causes additional problems relative to this Jensen inequality effect. And the paper quantifies some of this, but I would make that the first part of the paper. I would lead with this. But then there are people who don't rely purely on default observations to estimate default probabilities. So the paper's doing that. So you want to essentially preempt people criticizing you on that front. So you want to defend against a potential criticism and say, look, we know that if you just use the realized default probability, it's not a great estimate. We can get around that. But I think you probably can argue against this stuff. So further comments. So why do we care about this Jensen's inequality bias? We only care about it because it explains something. I don't think we have an inherent interest in the bias per se. So I have a paper showing that the bias is weaker at long maturities, and Peter's work nicely agrees with that. And that's quite interesting because it helps generate a flatter slope for a flatter slope for the term structure of spreads relative to using an individual representative firm approach. But this paper actually has results about 3 sets of maturities, whereas we only had 2. So I think it would be nice if Peter could explain something about the curvature of the term structure of credit spreads. So also I think it's important to go beyond mere documentation. The bias may be this big or that big, but why is the bias the way it is? And so I have some work showing that what matters for the size of the bias is the time evolution of the distribution of leverage. And that explains why the bias is different at different maturities. And if you just think about a simple series expansion, it's basically very similar to what we teach the students with utility and risk. Basically, think about the cross-sectional mean credit spread. It's equal to the representative firm spread plus a variance correction, a skewness correction, and so on. So the size of the Jensen's inequality bias is going to depend on the cross-sectional variance, the cross-sectional skewness, and so on, yeah, with respect to some characteristics such as leverage. It would be nice if you could relate the term structure, yeah, of credit spreads to some of these things. That would be interesting. For example, how does the variance, skewness, and kurtosis of leverage vary across credit ratings? Now, with such excellent data, I think it would be criminal not to do that. So further comments. So some people would say, yeah, the Merton model is a very simple model. People have used the same ideas to resolve the credit spread puzzle with more complicated models. Well, actually, you can turn this into a strength. So in the more complicated models that I've worked with, also Hui Chen has worked with, you've got endogenous leverage, dynamic debt structure, endogenous defaults, and it's very difficult then to fit that to transaction-level data. It's much easier with the Merton model. So a few other comments. I don't think it's wise to go and say the credit spread puzzle is a myth because many papers don't use a cross-section or don't have a long enough time series for default. So in addition to the work I've done, other people have done work basically using the cross-sectional approach and being careful about the estimating default probabilities. And it doesn't make sense to say we have almost no empirical estimates of the Jensen's inequality bias. If you read these papers and do simple, just take the ratio of two numbers, you'll be swimming in estimates for this bias. And it's important to acknowledge, I think, the intellectual debt owed to Caballero and his co-authors. So Caballero, I think, was one of the first to come up with this idea that using implications from an individual firm model is not a good way to understand aggregated variables. And he did that for investment. So it'd be nice to cite some of his work. And also acknowledge that cross-sectional heterogeneity is fundamental to understanding other things in finance. So Jonathan's here, so we can mention one of his papers. So in conclusion, I would say the paper's main weakness is that existing work already resolves the credit spread puzzle and also the risk premium puzzle by using a cross-section of firms and a long time series for defaults. But what are the paper's strengths? So there's an impressive empirical side to the paper, and this use of transaction-level data I particularly like. And also I like the fact they explicitly derive the variance of the expected default probability through the variance of the estimator. But I think they could do more work to fully exploit the data and build on the existing literature. And I think I've outlined some ways to do that.